about folded strings as a dual to SYK. Okay, so please stop me at any time if you have a question, and I'll try not to be over time. Okay, so raise your hand if you have seen SYK before. Okay, obviously, nearly everybody in the audience. But I'm still going to give you a recap. So this is a 0 plus 1 dimensional quantum mechanical theory, which consists of n Majorana fermions. So these are the psi variables. This I label index goes from 1 to capital N, and we're going to take n large. So this is going to be the only scaling that we do. This is going to give us enough headache, no double scaling in this talk. Okay, so each fermion can interact with any other fermion. Here's the Hamiltonian via this Q fermion interaction. We can change this Q. This is going to be our the parameter of our theory, and maybe I'll just use the blackboard or the green board to say to see how it's to show you how it's related to some other things. Okay, so these J's are random couplings, and we're going to sum over this randomness. The mean of J is 0, and J squared is some number that scales with n. Okay, so the propagator of the fermion is this time-ordered propagator here, and we are in Euclidean space for now, following the paper by Maldacena and Stanford from 2016. This is for free Majorana fermion. This is a simple calculation. You just get this sine function in tau, and in momentum space, you just have a 1 over the frequency for the propagator. Is this perfectly clear? Can I move on? Good. Mellon diagrams. So here's a propagator, and I'm just taking Q equal 4, so you have 4 fermions coupled in the Hamiltonian. So you're, I think I'm running out of battery here. Thank you. I think I stopped it with my own finger. So you have valence for vertices in these diagrams because we have Q equal 4 in this example. So you have a bunch of diagrams, and you can sum them up. Just solve the Schwinger-Dyson equations. You can define the self-energy sigma, and the propagator, the dress propagator here, G. This bit of these coupled equations are in Fourier space, and this is in real space. You can solve this numerically. Or a strong coupling, you can drop this I omega term here, and realize that your system, which is now these two equations, enjoys some time reparametrization symmetry. Tau goes to f of tau, and then G and sigma transform covariantly. You can try to solve this using an ansatz, which is this power law function for the dressed propagator GC. Okay, so you can plug this back into these equations, and then you can get some expression for B in terms of Q. And Q is just 1 over delta, or delta is 1 over Q. Maybe I just write this down here so that we remember. Okay, so I think this is familiar to most of you. What can you do? Well, you want to compute the operator spectrum in SYK. You can do that by looking at the 4-point function. And here's the 4-point function. Now, this comes with 4 indices, which could be all different, but you're going to get 0. Otherwise, you set them equal in a pairwise way. So I only have I here and JJ on these Majorana fermions. Then we can consider the average case as Maldacena and Stanford did, or Kitaev did. So I'm just summing over these I and J indices here and dividing by n squared. So the first disconnected part is this bit here. So that connects these two guys and these two. Okay, and we are going to be interested in the connected part, which is suppressed by large n, the number of fermions, and this I'm going to look at all these diagrams separately. So the first one is F naught, that's the disconnected part in this expression F here. And I'm just multiplying the two propagators here. And I did not draw it in this diagram, but you also have to cross the legs, and then you add an extra minus sign here. Okay, so there are more diagrams than what you see here. So if I have a diagram like that, how do I get the second one? Well, I have to use a graph building operator, which is this integral operator. Basically, I'm adding one rung to this ladder. Okay, so I have to integrate over this time here and that time there. These are these two integrals. And so this takes this Fn diagram and then creates the Fn plus 1 ladder diagram with one extra rung. And this K here, the kernel for the ladder is, I have Q minus 2 of these vertical legs. Here in this case, this is just 2, because Q is equal to 4. And I'm adding also these two extra propagators here along the ladder. Okay, so this is the kernel. And you want to solve this. You want to sum up all the diagrams. So how Maldacena and Stanford did it, they realized that the kernel commuted with the Casimir for the two particles, and therefore the eigenfunctions of the Casimir will be the eigenfunctions of the ladder kernel as well. Okay, so here is the conformal 3-point function for this one-dimensional CFT, and you can just compute the eigenvalues for this graph building operator. You just integrate it against the kernel, and the eigenvalue is a little bit horrible, but you can compute it exactly just by performing this integral, where K is the kernel from the previous slide. Okay, and then the operator spectrum is given by wherever this eigenvalue is equal to 1. Okay, so for Q equal 4, for fermions in the Hamiltonian, you're going to get this series, more or less integer spaced. Starts with h equal 2, that is related to gravity. But in this talk, we're going to be more interested in all the other operator dimensions. And we'd like to today find some theory that reproduces this, or basically this horror in that box as a dual to SYK. Okay, so that's the plan. I have some other projects on SYK. Please check out my student James's poster on Krylov complexity that is, of course, very much related to the previous talk. Okay, so this is SYK, and what is the holographic dual? That's the question that I'd like to ask beyond JT gravity. Here is a screenshot from a paper by Maldacena and Stanford from I don't know which page, it's at the end, before the countless appendices, where they sort of speculate about the nature of the dual theory. And they have this sort of diagram here. So this is ADS2 with the two boundaries, these vertical lines. And in between, you have some quarks and some flux tube connecting them. And so they claim, or they say, that the dual must be something like the 't Hooft model, but in ADS2. Okay, so raise your hand if you know what the 't Hooft model is. There should be more hands than before. This is a 51-year-old theory by 't Hooft. So it's large and QCD in 2 dimensions, but in the planar limit. So basically the first application of the planar diagrams, he managed to sum up all the planar diagrams and came up with an equation for the quark-antiquark band state. So you can compute the spectrum for the meson from the 't Hooft equation, which is right here. I'm not going to sum up planar diagrams. I'm just going to derive this equation for you for free. Well, you pay the registration fee. Just by looking at this two-particle system and connected by a linear potential. Okay, you can just get it from there without QCD. So what I have is two particles, massive particles. Later we're going to set the masses to 0, connected by some string or a linear potential. So I can build a Hamiltonian like this. Okay, here is the linear potential connecting the two particles at x1 and x2. I'd like to quantize the system. You cannot really do that in the lab frame because you're going to run into anomalies for the Poincaré group. Instead, what you can do is you can boost the system and go to a light front picture. And then you can compute the invariant mass by taking the square of this Hamiltonian and minus the total momentum squared. And then if you infinitely boost the system, so both particles move with the speed of light towards the exit, then you get this formula for the mass squared. Okay, well, so M1 and M2 are the masses of the quarks. These are the renormalized masses in the 't Hooft model. What is the Z here and the S? Well, Z is this momentum fraction, this ratio. How much momentum does the first particle carry out of the total momentum? Okay, and S is a canonical conjugate variable. Okay, so this is not giving you this equation just yet. Well, first of all, you want to quantize it, so you want to take the left-hand side and the right-hand side and let it act on some wave function, and we are going to go to the Z basis. So I take this phi of Z function, and I know how M squared acts on it, just multiply by M squared, and the right-hand side is more complicated because here you have the absolute value of the canonical conjugate. So this absolute value is precisely this absolute value here, same thing. So you go to Fourier space, you take the absolute value, you Fourier transform back, and then you end up with this principal value integral. Okay, it's an easy calculation. And the integral does not go from minus infinity to plus infinity because you have to do an extra projection on positive momenta. Otherwise, again, I mean, in quantum mechanics, these negative energy modes are hard to interpret. So that's something you put in by hand. But in 't Hooft's original paper, of course, it just comes out of QCD. So this is the 't Hooft equation with two masses. We can set these masses to 0. That will be relevant for SYK. Beautiful. Let me try connecting this again. Fantastic. So this is the 't Hooft equation. We set this term to 0. But then this is still a bit horrible, and exact solutions are not known. You can compute it numerically easily. It was done in the 70s. And you get this sort of spectrum, linear-ish Regge trajectory. Starts with these 3 quarters here, so it's not, WKB doesn't quite work here. But anyway, it's not exactly linear, so it's a bit complicated. And all this complication comes from the fact that you took this absolute value. Okay, so this is not the dual of SYK. This just gives you the wrong spectrum. You can try to put it into ADS2, which is what we're going to do next. But the spectrum will be still complicated. So you have to simplify it somehow. This looks horrible, but it's still much, much simpler than the 't Hooft model spectrum. Okay, so let's try to put it into ADS2. Any questions so far? Okay, so I have two particles connected by a string, or I can also just talk about folded strings, more or less the same thing. Just consider the non-Bugoto theory in ADS2. Okay, so but what are these particles, these quarks I described earlier? We can just for a moment try to think about a higher dimensional setup. Let's say you are in 2+1 dimensions. Okay, so here's a non-Bugoto string. Let's say these horizontal bits are static, and there is this vertical piece which moves with some velocity, perpendicular velocity v. Okay, less than the speed of light, obviously. But what I'm going to do is I'm going to boost this to the right, but shrink its size, its length at the same time. Okay, so at the end, I'm going to end up with a particle with a finite momentum and finite energy. There is such a limit. Okay, so these are the particles that, the two quarks of the 't Hooft model. And now we are in 1+1 dimensions. Okay, so when I'm drawing some folded string like this, all these 4 blue particles came from a limit like that. You can think about it that way. Okay, so actually I have an animation. Do you want to see it? I did not hear a no, so I might as well show it. Not I'll talk. It has to be the anim folder. Okay, so that would be like a folded string moving in 1D. I separated vertically the particles a little bit so that we actually see something. Particles, when they run out of momentum, they sort of bounce back. They always move with the speed of light, but there are these bounces when the momentum vanishes. Okay, so that would be a folded string with 4 particles. For SYK, for kinematical reasons, we are interested in the case with only 2 particles. Because the Feynman diagrams are somehow such that they cannot bound more than 2 particles. Okay, so when particles collide, nothing happens, they just pass through each other. And these are the bounces. So when this is the higher dimensional picture, you have these 2 strings pulling the particle back. And the particle is either this blue blob or this vertical little piece of string, depends on how you think about it. And when it runs out of momentum, it just starts moving in the opposite direction with the speed of light. Okay, is this clear, roughly? So in terms of equations, there's an older paper by Söderberg, Anderson, and Gustafsson, the Lund group from 40 years ago. They constructed models like this in flat 1+1 dimensional space. So you can go to, so take the number, go to theory. You can go to some temporal conformal gauge. So the worksheet is parameterized by tau and sigma, and you set tau equal t, the target space time, okay, in Minkowski time. And the embedding is parameterized then by this x of tau and sigma variable. Okay, so everybody has seen this equation of motion before, very simple, but there are also constraints. This is string theory that this embedding function x has to satisfy. But it's easy to satisfy these using what they call the directrix function A. That's a function of 1 variable. And then you build the wave like that, some left and right moving waves, but the derivative of A has to be either plus or minus 1. Okay, due to these constraints. So here is an example for A, plus 1, minus 1, plus 1, minus 1 derivative. Does not have to be periodic. And when I build this embedding function, which is on the right-hand side, this is a 3D plot. It's not sure if it's visible. Not really. You get some, two-dimensional function, some graph over a 2D plane, and there are these planes here. So the colors don't come out, right? So there are blue patches. This one is blue, and believe me, this one is blue as well. This is blue, and there are some gray ones like this one, etc. So the blue ones are special because if you go through this little exercise, the sigma derivative of the blue patches is 0. What does it mean? Should I point at people? It means that that patch is mapped into just a 1-dimensional line in target space because the sigma derivative vanishes. Okay, so these are precisely those blue particles from the previous slide. So there are 2 types of patches, and that's the only thing that I want you to remember from this slide. The gray ones are proper string embeddings, 2-dimensional patches mapped into a 2-dimensional patch on target space. But the blue ones are mapped into 1-dimensional word line for the particles. Okay, so there are these, there is this kind of structure here. Is this clear? Should I say more words about it? Okay, so this diagram is the only important part. And believe it or not, the same thing generalizes to ADS2. Okay, so now here is the worksheet of a 4-particle system. So 4 particles in a chain connected by straight string segments. And okay, so there are these blue patches, and these are all mapped into the word lines of the particles, which move with the speed of light. And these white and gray patches are the strings stretching between them. Okay, so if I take a time slice like this, here is a particle, there is a string connecting it to the next particle, there is another string connecting it to the next, etc. And these dashed lines should be identified. Okay, so what else is in the picture? There are some variables here. So what are these variables? And here is the figure that explains it. So let's take this patch here, right? That's a proper string patch, worksheet patch, and it's mapped into ADS2. So this is ADS2, here are the boundaries. And the way I define these numbers here is I take the boundaries of that worksheet patch. So these are the particles. They move with the speed of light, so they are at 45-degree angles. So I get a diamond like that. And I just continue these lines, and I hit the boundary at some point. And I take the time and put it there, and so on. So I get 4 times banding the diamond, okay? So these 4 time values are precisely these 4. You can also think of just light cone coordinates, doesn't matter. I prefer to think about it in like a holographic way. You'll see why. Okay, you have 4 patches, so you can continue, you can build these time variables all over the worksheet. Okay, so this is supposed to be some kind of solution in the number-Goto theory. So what's the action? Action is just the area. Let's compute the area. This is it. Okay, I'm not telling you the calculation, homework exercise. The area of this patch in terms of these 4 time variables is just this cross ratio and log of that. Okay, what's the area? What's the total string action? It's just the sum of all the areas. These guys are mapped into 1D lines, so these don't contribute at all. So I just need to add up the areas for the actual strings. Okay, so when I do that, I get a bunch of logs with plus or minus signs, depends on whether these links come from the numerator or the denominator. Okay, so this is the action. So basically what you have to do, if these are spatially separated, they come with a plus sign, so plus log of this, the difference of these two. And if they are vertically separated, time-like separated, they come with a minus sign. That's it. And you can determine the prefactor, it is 4. Okay, so that's the action of this sort of segmented or folded string in ADS2. Any questions about that? Yes. In the target space, these are 1D lines, the particle word lines. On the worksheet, not really. I should actually, I should mention that Itzhak Bars also had this kind of structure in his papers.
So there is no like an effective mass which is continuous or anything.
Mass in what sense? These are all massless particles, if you wish.
Yeah, but the size of the blue patches don't matter for anything.
Not really, not here. We're gonna forget about the worksheet and just take this integer lattice with the time variables on it. So we kind of fix some conformal gauge here. Any other questions? I'm going too fast. I might have to repeat stuff.
You still need to integrate at the end of the day over all these times to do the path integral over all possible worldsheets, or?
The path integral is coming up. Yes, I'll talk about that in 2 slides. But okay, so if you have the action, you might as well just write down the equation of motion, which is this. Very simple. If the enemy gives you 2 rows of these time variables, then you can just evolve the system forward or backward. Basically, this equation of motion combines 5 neighboring time variables. So let's say from these 4, you can compute the 5th one, and then you just evolve the system forward. This thing also works for segmented strings in ADS3. For some reason, where these time variables are sort of x plus variables on the boundary Minkowski, 2-dimensional Minkowski space. Okay, you can solve it and plot the result in ADS2. And this is a 2-particle system, so global time is towards the right. And then, of course, your string just oscillates and moves in this box that we call ADS2. For 4 particles, the system does some more drastic oscillation, and these are all non-periodic. These are periodic in flat space, but not periodic in ADS. Okay, so here is the path integral. So what do we do? And this is going to give us the sort of the first hint that this theory might have to do with SYK. So this was the classical action. Again, these logs of the differences of these time variables, neighboring time variables. And I multiplied the action by this that is usually denoted by G. So this is the radius squared of ADS, so R squared, divided by 2 pi alpha prime. So in the integrability literature, this is typically denoted by G. Okay, so I somehow want to build a path integral out of this classical action, and I demand that it's invariant under global SL2, which acts on the time variables via this Möbius transformation. And A, B, C, D, so these are just some unit determinant matrix elements. Just to simplify the notation a bit, I picked some T and M somewhere on the lattice. I denote that by T, and T tilde is just the next one, one forward time step, okay? So when I write down the path integral under an SL2 transformation, the Jacobian is given, oops, here. What happened? And I want to cancel this Ct plus D squared from the denominator. So I need to introduce some extra bit here so that the measure is SL2 invariant, because the action is SL2 invariant. These are some cross ratios. So you can figure out how T minus T tilde the next guy transforms, and you get this, this factor. But there is also the previous, T minus T tilde, so I'm talking about these 2 guys, and there is this guy as well, so that contributes an extra factor like that, so that can cancel this Jacobian. So it's enough to include one of these links in the denominator. So now the measure is invariant under SL2. The action was invariant, so this is an SL2 invariant path integral. And we are in Lorentzian space, Lorentzian signature. So what should I do next? If you just look at this path integral. Any ideas? I'm not going to talk about the Schwarzian. The Schwarzian has a, thank you by the way for the comment, I forgot to put it here. This measure is in the Witten Stanford paper in the appendix, the same measure that they use for the Schwarzian path integral, but they have a different action. No logs. I have logs. What else do I have? I have an exponential. Why not cancel the 2, right? So if I do that, and I set this G to a specific value, I get some propagators. And I can set this G so that I precisely get the SYK ladder diagrams in Euclidean space. Now here are the ladder diagrams again. Here's the path integral. And this is what I'm going to do. I'm going to set a G equal I over 4, 1 minus 2 delta. So Q was the number of fermions in the Hamiltonian. So this G is imaginary. Remember, G was the radius squared over 2 pi alpha prime. So I'm doing something illegal here. arrest me. Also, I have to set the number of course, the number of particles to 2 because SYK only combines two fermions. Okay, so if you plug this in here, you get precisely the SYK kernel over and over again. Okay, but the SYK calculation was in Euclidean. We are in Lorentzian, so something does not quite add up. So I'm not claiming that this is victory. I'm just claiming that this is a hint that we are on maybe not the right, we are on some path. Okay. Furthermore, we are not getting the signs here in the SYK kernel because this is an inherently bosonic system, so you kind of, this is going to be the theme. We are looking at a quantum mechanical system. You have to do this anti-symmetrization by hand. Okay, you can do that. Any questions? This is the last time I talk about the path integral, so.
So the flux tube is a U1 flux tube, or it's related to the gravity sector, or?
I'm talking about the non-Bogotá string.
Okay, but usually you think about some effective string that's associated maybe with some confining.
You can think about it that
some
way.
gauge flux.
Yes.
So I should think about it as having some U1 gauge field in the bulk, or some remnant of
I think
the UN.
it would be a large N
gravity.
QCD flux tube in the bulk.
Because you usually think about these ladders as somehow associated with gravity back reaction, not as an additional gauge field.
I mean, we are on a rigid, I want to think about it as a rigid ADS2. We are like strictly in the conformal point. So gravity does not show up in this talk. Any other question about the path integral? I could sort of fork here and talk about the 6-point functions of Rosenhaus and Gross, but I'm not going to. I'm just going to mention that this might be some kind of correspondence, folded string in ADS2, or Toff model in ADS2, but with this imaginary radius squared, is somehow related to the SYK theory. Yes?
Can you go back to this? Sure. So this path integral computes a number as it stands. Are you suggesting that, what is the meaning of the spectrum?
It's a very good question. I don't know. This is just a hint. I'm going to switch gears now, or maybe to a lower gear, and I'm going to talk about the Hamiltonian formalism. I cannot say anything else about this. This is what I know. Okay, so what do we need for the Hamiltonian formalism? Well, we need the Poisson brackets, and we need the Hamiltonian. So how do I compute the Poisson brackets for these time variables? Okay, raise your hand if you know what the Pyros bracket is. Damn, Merolf is not here, but he knew. Okay, a few people. Okay, so this goes back to the 1950s, when Pyros realized that you can actually take a Lagrangian for relativistic field theory, and whatever it is, let's say it's 2 derivative action, and you can get the Poisson brackets just by a simple calculation. Here is a Lagrangian in d dimensions, and your local field is phi. And then you're interested into observables f and g, and the question is, what is their Poisson bracket? So what you do is you compute this derivative. So what is it? Well, there is this delta g of phi appearing in this formula. So first I have to tell you what it is. So we're going to construct this delta g of phi by deforming the action. So this is the original action, and I'm subtracting minus k, some small parameter, times g, the second guy in the bracket. Okay, so I added this source for g, and then I look for two field perturbations. So this changes the equation of motion. And you can compute a retarded perturbation, which is the same as the original field, some solution in the past, and then it varies in the future. And you can also compute the advanced perturbation delta phi A, which is the same as your original solution phi in the future, but it can be different in the past. So we are in a relativistic theory, so these are well-defined statements. And we are interested in these perturbations up to a linear level. And then this delta G of phi is just the difference of these two field perturbations. Okay, and then you just take F evaluated on this perturbed field phi plus k times delta G phi, and just look at its derivative in terms of k. Okay, so Pyers introduced this for continuum field theory, but actually it also works for discrete theories like this one, because this is also a relativistic theory. It inherited relativistic properties from the Nambu-Goto theory. So here's my equation of motion, and I can perturb it as the recipe says, and compute the Poisson bracket, and I get this for two neighboring time variables. So it's a quadratic bracket. It's not entirely trivial. By the way, it also showed up in a paper by Gechtmann from 2014, but there was no physics interpretation. Sorry? It is antisymmetric. If you, well, it depends. Well, we're gonna set G imaginary, so. Okay, the other thing we need is the Hamiltonian. So just to motivate the Hamiltonian, which is gonna be the Casimir, I'm gonna go back to flat space, and I'm gonna go to light cone frame. Okay, so the light cone, in the light cone frame, the H minus Hamiltonian is given here. And the second part is the interaction, which is just the difference, the distance between the two particles. And you can also write it down, so x plus is your time variable. You can also write it down, H plus, the other, in terms of the other light cone variable x minus, taken as time, and then you get this formula. You just replace the pluses and minuses. Okay, and then you can try to get some invariant mass for this two-particle object by multiplying the two Hamiltonians. And we are interested in the zero mass limit, zero mass for the particles at the endpoints. So I can just naively set them to 0. And what I'm ending up with this, the product of these two terms. So this is it. Okay, so what you see here is basically the distance squared of these two turning points. So you can play the same game in ADS. You can, here is the worksheet for two particles. And basically you're interested in this point here and that point and the distance squared. So Pavel kindly gave us the formula. Cosh of the geodesic distance is equal to the product of the two vectors corresponding to these points in embedding space up to minus sign. And you can also compute the Hamiltonian in lab frame. So Gobser has done that. The potential has a sinh of the geodesic distance divided by 2 in it. You plug everything in there, and this is what you end up with. Okay, so the mass squared is, in terms of these time variables, is given by this cross ratio. Okay, so I have some Poisson brackets. I have some Hamiltonian. I can take those time variables and build canonical variables. And in terms of these variables, I can write down some SL2 generators for this ADS2 space. And notice that I'm in momentum space. So everything, I quantized everything in terms of these P's. And before quantization, if I just take the quadratic Casimir, then I get this Hamiltonian back. So the Casimir is the Hamiltonian, and in fact it generalizes to n particles that you can compute from the spectral curve. That's a bit more complicated. I won't discuss it. Okay, but at the quantum level, you can just take these generators and write down this Schrödinger equation. So instead of m squared, I plugged in h times h minus 1. H is the conformal dimension of the combined system. And this phi of z is your wave function, and z again is this momentum fraction variable. How much momentum does the first particle carry out of the total momentum? Okay, so is this equation familiar? Well, this is just the Peschel-Teller equation after coordinate change and some rescaling of the wave function. And notice that this is the Peschel-Teller, but it's a strongly attractive Peschel-Teller. So the potential is like that, with 1 over x squared type singularity at the endpoints. So there is a beautiful story here with renormalization in quantum mechanics that I'm not telling you about. But we want to set this G to imaginary values anyway. So that turns this potential into a repulsive potential. Okay, so you can compute what's the behavior, what is the behavior at the endpoints, and you get some parallel behavior with some coefficients. And if you set the coefficients in an appropriate way, this is a perfectly normal standard quantum mechanics condition on the wave function, then this equation gives precisely the SYK operator spectrum. Okay, so this is in this paper from last year, where I did not discuss these Poisson brackets or the Casimir, etc. I got this equation in a different way. Any questions? So I claim that in some sense this is a dual to SYK, to the 4-point function calculation. This is a kind of a cousin of the 't Hooft model, or what the 't Hooft model would be in ADS2. But the point is that we have neglected this bit here when we took the product. And these actually matter. When you compute the time evolution for these particles, these kinetic terms will be responsible for these jumps in the particle positions. So kind of you can think about it that these are responsible for the discrete time steps. So if you don't consider these guys, then you're kind of stuck on a as far as discrete time goes, stuck on the same time slice. And okay, so if I take G imaginary, then my canonical variables x and p can still be real if I consider these time variables to be complex conjugates of each other. So this guy is a complex conjugate of this, and this is the complex conjugate of this. So this would be the complex conjugate of this guy. So you're kind of on the same real time, but different in imaginary time. That's the kind of interpretation. And the phase space would be some, for this two-particle system, the square of the hyperbolic plane. Okay, so how much time do I have? 0 minutes. This is my summary slide. So the Sachdev-Ye-Kitaev model has this Hamiltonian. I didn't talk about it, but these ladder diagrams are of the fishnet type. Okay, so the fishnet or fishing net Feynman diagrams look like this. This is just a picture from Zamolodchikov's paper. And he realized that these are integrable. So you can actually embed these SYK diagrams into larger integrable model. And integrability, of course, very constrained, so that constrains the properties of SYK. I put quote marks around folded strings. I don't know if you want to consider this system that I described for a folded string, because it has these imaginary radius squared variables. It's a quantum mechanical system, a perfectly ordinary quantum mechanical system that reproduces the SYK spectrum. And then we use these boundary time variables. The advantage of this is that these are not constrained. So I just computed the Poisson brackets. There were no direct brackets in this talk. And another take-home message is that you want to go to momentum space when you discuss this CFT, this one-dimensional CFT. There aren't a lot of papers about CFTs in momentum space. There should be more. One more comment about these string bits, the two particles connected by the string, is that these are not in discrete series representations of SL2, because we set the boundary condition in terms of that Z variable. So what it translates to in terms of the P space, we don't have discrete series representations, but that's okay. Particles don't need to be in unitary EREPs unless they are free. And you can check if you set the string length to infinity, so alpha prime to infinity, you get delta equal 1/2, and you do get discrete series representations. And here are some future projects. You can, of course, generalize these ideas to more than two particles. These would be some kind of duals to fishnet theories. There has already been a so-called fish chain model, which is a dual to these fishnet theories. So by Gromov and Sever 6 years ago. So the question is, what is the relationship between these fish chain models and this theory? You can also generalize it to higher dimensions, or try to generalize it to higher D. And finally, I think maybe this could be the most important, is to try to enlarge the size of ADS2. So ADS2 has this imaginary radius squared here, but I want a positive R squared. Okay, so for that I would need a delta that is would be more along the lines of the principal series. And you would have to tackle this problem with the discrete time steps in order not to have instabilities when you set delta equal 1/2 plus I times a number. Okay, that's it. Thanks.
Questions?
So Rami, the multi-particle states that they computed from the 4-point function in the ordered channel or auto channel, or it doesn't really make a difference?
I don't have a picture for that. So it's two lines is the S.
Okay, but you don't have, what's the relation between the tau, the different taus? Is it auto or not, or it doesn't matter?
Oh, well, you can analytically continue this. In fact, they did that.
Yeah, but somehow you ask about, where do these, in which physical sheet, in which sheet do these poles really show up, or something like that, no? Well, maybe it doesn't.
Here,
Yeah,
this
maybe
was time ordered, so and then you analytically continue to the OTAC if you want. But to get the operator spectrum, you didn't need that.
Any other questions? Maybe a quick question. So this Pios bracket, you need to restrict it to solutions of the field equations, which are these annoying nonlinear equations. But did you then restrict to just four numbers or so, or is that something?
So the way you do it is, okay, so I source it here.
Yeah.
Because let's say I want to compute the commutator of these two guys.
No, my question was that this bracket should only be applied to the set of T's that solve that equation, right? The field equation. Because that's where the bracket is defined to begin with. So you would have to solve
right,
these.
So I would need to pick two rows, and that's my phase space. And my bracket would be sort of applied.
And those are not constrained by the field equation?
No.
Okay.
Because it relates 5, like I3.
To the next. Yeah. Okay. If there are no more questions, let's thank David again. And we come back.